Okay, let's start again. So we have the pleasure to have today someone we have known for a long time, who has been away for a long time in the States, in Caltech. No real need to introduce Jean-Philippe Avouac. So he just came back and is now head of the IPGP. Has done a lot of work in Asia since his PhD, and of course afterward he did a lot of work elsewhere. But he's coming back to his first part of his career. He's never left actually Asia. You have always worked there. C'est mort. Okay, so Jean-Philippe.
Thank you, Laurent. So I hope it's going to wake up automatically. Yeah, okay, it does. So thank you for the introduction. I wanted to thank the organizers for the invitation to speak at this event. It's a big honor. So we are here today to celebrate the contributions of Xavier Le Pichon. So I haven't had the privilege to work directly with Xavier, but I was hosted by ENS when I was at the Commissariat à l'énergie atomique, so I had a courtesy appointment, and I must say I benefited a lot from this appointment. I could interact with many of you in the room and recruit some bright students. And also I was attending regularly the lectures at Collège de France, and I must say that it has been an important source of inspiration in my research. The talk I will be presenting today will draw also from work of other giants who actually passed away over the last few years. So Paul Taponnier, who was my PhD advisor at IPGP, Peter Molnar, best friend, best foe with Paul Taponnier, and Jeff King, who unfortunately passed away a few weeks ago, and actually his funerals are held today in London. So going back to about 60 years ago, where plate tectonics was put together, people figured out quite quickly that earthquakes were aligned along plate boundaries, and that they were the result of incremental displacement at plate boundaries. So, for example, if you take the example of the Sunda subduction zone, the Indian plate is subducting beneath Sumatra. For a long period of time, the interface is locked, stress is building up, the fore arc is being squeezed horizontally, dragged down, and then at some point, the stress at the interface cannot be balanced by frictional resistance, and it slips and radiates seismic wave and tsunami waves. So this is well understood, and Serge gave us a great review on that topic. So we can monitor this process today with geodesy, and so we can map where actually the interface is locked and where there is stress building up and where the interface is actually creeping. We know that some of these places with very low seismic coupling actually should not produce large earthquakes simply because they are creeping, right? So in the early days of plate tectonics, we thought that earthquake forecasting was more or less at hand. And now we realize that it's a complicated problem. Even with the help with geodesy, we are not at the point that we can make any useful forecast. And this is the topic I'm going to talk about, not in the context of subduction zone of global tectonics, but in the context of continental deformation. So in the India-Asia collision zone. So first, let's notice that when you go from the Sunda subduction zone to the India-Asia collision zone, we see that the seismicity is widespread, and so is the topography. So let's say a few words about how this continental deformation actually relate to plate tectonics. So we heard already a little bit about the Indian Ocean. So we know about the distribution of the age of the seafloor in the Indian Ocean, and based on that, we know that about 150 million years ago, India was actually attached to Antarctica and Africa, rifted away from both, and then traveled north as the Tethys Ocean was being subducted beneath Eurasia. About 50 million years ago, the continental collision started, and from there on, continental deformation occurred. The slab detached from the continent because of being less buoyant than the continental crust, and once the continental crust is not dragged anymore by the slab pool, it starts to jam into the crust of Eurasia. And that's the reason you have widespread deformation. So widespread deformation doesn't mean that actually deformation is distributed homogeneously. With geodesy today, we can actually map the strain field. So here on the left, you have velocities relative to Eurasia determined from GPS measurement, mostly permanent, so continuously recording GPS stations. And on the right, you have the strain rate map, so it's the second invariant of the horizontal strain rate tensor. And what you see from this map is that it is heterogeneous. You have strain concentrated along the north, along the Himalayan arc, and on the edges of India. So obviously, there is concentration along major fault within that collision zone. And it's interesting to see then how this relates to earthquakes and whether we can use this information to say anything about future earthquakes. So let's first look at past earthquakes. So not surprisingly, the large earthquakes in the area all fall in this area of high strain rate, including the Assam earthquake, 8.7 from 1950, which happens to be the largest continental earthquake ever recorded. If you look at the large earthquakes which have occurred in the area since the beginning of this century, they nearly all of them fall in this zone of high strain rate, including the Wenshuan earthquake in the Longmenchan area, and the Kashmir earthquake in northern Pakistan. Both of them killed about 80,000 people, and it includes also the most recent earthquake, the Mandalay earthquake from last year. And here I'm showing a measurement of surface displacement obtained from correlating images collected before and after the earthquake. And the map is showing the north-south component of the displacement. Blue is north and red is south. And you see that there's a discontinuity, a sharp discontinuity that is really straight, that runs for about 710 kilometers. This is the longest continental earthquakes ever documented. Let's move now to the Nepal earthquake, the Gorkha earthquake of 2015. So when you combine information of surface deformation from remote sensing, like I've just shown, which you may obtain from optical or from SAR images or radar images, with seismology, you can actually produce relatively detailed models of how earthquakes initiate and propagate and rupture. So this was possible to do for the Gorkha earthquake, because actually the earthquake occurred beneath a number of permanent stations that we had deployed in Nepal. So here you see one of those stations, and on top you have the vertical displacement recorded at that station, and here this is the horizontal displacement recorded at that station. 0 is the origin time of the earthquakes according to seismology. So what you see is that nothing happened at this station, which is actually close to Kathmandu, because the earthquake started actually west of Kathmandu, about 100 kilometers away from Kathmandu, propagated towards Kathmandu, and then the ground moved up. There was an increment of uplift in the Himalaya and south. So you had an increment of thrusting of the Himalaya over India. So with such data and the remote sensing data, you can produce models that describe how the earthquake actually unfolded. So it started west of Kathmandu, and what is plotted here is the slip rate on the fault. I didn't say the focal mechanism indicates that it's nearly a horizontal fault, and at a depth of about 8 kilometers beneath Kathmandu Valley. So it shows that you have a slip pulse that started at the epicenter and propagated east at a rate of about 2.8 kilometers per second. So these observations are extremely important, actually, to start to build physics-based model of earthquake, which we are going to use in earthquake simulators, and I will show that a little later. So let's say a few words about the geological context of the Gorkha earthquake. So here you have a cross-section across the Himalaya at the longitude of Kathmandu. And so what we know is that we have a wedge with a number of thrust faults, and the main fault is the one that emerges at the front of the Himalaya, the main Himalayan thrust. And so the main fault is this one, right, that runs at a depth of 8 kilometers beneath Kathmandu, en route into mid-crustal detachment beneath southern Tibet. So we know from geodesy that this fault is locked, but that there is about 2 centimeters of shortening across the range. And from the inversion of the geodetic data, we can map the area where the fault is actually locked and where it transitioned to creep. So at about 120 kilometers away from the MHD at the surface, the temperature is high enough in the crust, maybe 350 degrees, and you start to enter the ductile domain, and the fault is creeping. So we see that very clearly from geodesy. So on top here, you do have a map. The shading is showing the coupling of the MHD in the interseismic period derived from geodesy. The dots are showing the earthquakes, and you see that most of the earthquakes are at the lower edge of the locked fault zone where stress is building up. So now when we place this earthquake, the Gorkha earthquake, in this context, what we see is that it activated the deeper part of the locked fault zone, but this earthquake didn't manage to propagate all the way to the surface. We know that occasionally earthquake propagate all the way to the surface because the slip rate on the fault here is 2 centimeters per year, which is the same as the shortening rate across the entire range. So we know that on the long run, earthquakes must actually activate the whole thing. This earthquake is actually a small earthquake by Himalayan standard. You can see that the rupture area is relatively small, so a 7.8 earthquake is small by Himalayan standard. So in terms of explaining the geology. So one question is actually, what kind of largest earthquake shall we expect along the Himalayan arc, and how frequent should they be? So this plot is showing the magnitude frequency distribution of earthquakes along the Himalaya. So this is a traditional Gutenberg-Richter plot. So here you have the number of earthquakes above a certain magnitude, which is actually the horizontal axis, and this is a decimal log. So when we plot the data this way, we see that we have a regular decrease, and the slope of that curve is called the b-value of journey of 1. So the question is where to end that distribution. And one way to look at that is to balance the deficit of moment in the interseismic moment with the moment released by earthquakes. So the way we do that is that we integrate the deficit of slip on the locked portion of the fault, and we multiply by the shear modulus, and that gives you a rate of moment release that the earthquake have to balance, so that in the long run the fault would everywhere slip at the geological or geodetic rate. So in this plot, so this is the blue line when you do that here. And here what is shown is the moment released by earthquakes when we cumulate the moment up to the magnitude that is indicated here. So if we go all the way to magnitude 7.8, the magnitude of the Gorka earthquake, we see that it's still a factor of 10 below the rate at which the moment deficit is building up in the interseismic period. This is a log, decimal log rate. So we are far from balancing the moment budget or the strain budget, it's equivalent, with magnitude 7.8. We need much larger earthquake. Of course, we know that we had a 8.7 at one end of the Himalayan arc in 1950, so it's not a big surprise that we need larger event. And then you can do an analysis of using the observed seismicity to constrain the magnitude frequency distribution and extrapolating to the largest moment so that you actually balance the moment budget. So when we do this analysis, we find that we need up to magnitude 9 earthquake. Okay. And there is geological evidence that very large slip events have occurred along the front of the Himalaya. So here I'm showing a result of a trenching study. Actually, Jan Klinger was part of that, with Paul Taponnier and Laurent Bollinger too were involved. And a number of trenches have now been opened at the front of the Himalaya, and they typically show evidence for sudden slip event of the order of 10, 15 meters. So we do have occasional very large earthquakes at the front of the Himalaya. So based on the moment balance I was describing earlier, you can calculate the probability of balancing the moment with a largest event not exceeding this, the value that is plotted here. 8.7 doesn't do the job. Even 8.7 doesn't balance the moment budget. You balance it at magnitude 9. So this is a bit worrisome. And the next question is, okay, if we can have magnitude 8.7 or 9 everywhere along the Himalayan arc, because this is what we need, not only in Assam, where might the next earthquake occur? And when? So let's start with the when question. So here you have a plot showing the cumulated moments released by earthquake as a function of time, going back to 1500. And we can see that on top of that, in yellow, this is the moment deficit derived from geodesy. So the two lines should coincide if the seismicity is actually release all the deficit of moment building up in the interseismic period. So we see that over the last century, we have a relatively good match, and this is essentially because of this Assam earthquake. When you go back to 1500, we have a huge deficit. So a lot of moment has accumulated that has not been released by large earthquakes over the last 500 years. So that brings two questions. The two must balance over a certain time scale. What is the time scale over which they do? Is it over, obviously it doesn't work over 500 years. Is it 10,000 years? Is it 1,000 years? This is going to be very important for time-dependent earthquake forecasting. And the next question is, can we say anything about where the next large earthquake in the Himalaya might happen? So a traditional way to address that question of where it might happen is to look at past earthquakes. And here you have a plot showing the time of the large earthquake derived from historical accounts on some trenching. And this is descent along the Himalayan arc. And when you look at that plot, you see that actually this central area that produced a very large earthquake in 1505 hasn't repeated for 500 years. So we have about 10 meters of deficit of slip that has accumulated in that area, and the fault is fully locked. There's a more minor gap here. So it might be tempting to say, okay, this might be the place of the next large earthquakes in the Himalaya. We know that this approach doesn't work very well. People have tested this kind of approach for subduction zone, and actually it's a failure. So it's not a straightforward problem. So that's where we need to, and actually we can look at that problem in the context of the sagging fault. So the fault along which India is moving north relative to Southeast Asia. So the map is flipped, right? North is to the left here. And I'm showing again the rupture from the Morbidelli earthquake from last year, this 710 long rupture with about 4 to 5 meters of slip on average along the fault. And actually this fault was known to have a well-identified seismic gap. And the yellow patch show where is this seismic gap based on past earthquakes. You can see that the earthquake from last year ruptured the gap as expected, but also extended outside the gap and re-ruptured the area that had ruptured not so long ago in the 30s and here in the 50s on both sides of the fault. So there's not a unique relationship. It's the segmentation, the extent of rupture varies a lot, and Serge talked about that earlier. So that's where we need physics. We need to bring some physics so that we can actually produce this kind of complexity with earthquake simulators and maybe hopefully inform those earthquake simulators with observation, past earthquake, geodetic information, and so on. So this is the work we've been trying to do. So let's say a few words about the principle of those earthquake simulators. So first you need a condition for slip to occur on the fault, and this is based on the simple Coulomb friction model. Okay. And so if you plot the shear stress here, the effective normal stress, so the normal stress minus the pore pressure, you consider a fault with a various orientation in space. We know that a fault would be activated if you reach a failure envelope that can be described to first order by a straight line, which is the Moore-Coulomb criterion. So we know based on that to evaluate if a fault is brought closer or farther away from rupture, we can use the Coulomb stress changes, which is actually the change in shear stress on the fault minus friction times the change of normal stress. So you can activate a fault by increasing the shear stress, decreasing the normal stress, or increasing the pore pressure on the fault. This is well known. So this is a basic principle of what we are doing. Then you need a model that's going to describe how friction is evolving during slip. So the simplest model you can think of is a sudden drop from a static friction to a dynamic friction. And you need the dynamic friction to be lower than the static friction to have a stick-stick behavior, right? So here I'm showing an experiment done by my favorite and youngest student, my 2 daughters from 15 years ago. So this is a point process, right? And if earthquake were behaving like that, then it would be very simple to predict earthquake. You would have, if you turn the crank at a constant rate, you build up stress until you reach the limit for friction, then you drop to dynamic friction, and it would repeat, and in absence of interactions between fault, it would be a periodic behavior. So we know that earthquakes don't behave like that, first because you have a population of earthquake. So let's first think of a population of earthquake that would not actually interact. This actually mechanism would predict that the seismicity rate would be actually proportional to the stress rate, the rate at which you're turning the crank. So if you have a population of faults that are at different stages in their seismic cycle, and you load them at a constant rate, you expect the seismicity rate to be proportional to the strain rate. This is a prediction from that very simple model. So we can actually test whether that very simple logic applies to observation. So here is a simple exercise. You take the strain rate map that I've shown earlier, then you bin into values of strain rate, you count all the earthquakes in each bin, and you look at how the seismicity rate correlates with the strain rate. And it's a straight line. Okay, so it works. The seismicity rate is proportional to the strain rate, and here I'm assuming that the deformation at the surface is essentially elastic deformation. Strain rate and elastic stress buildup are supposed to be the same thing. So we would like to test also in time. This is a test of the model in space. We would like to also verify that in time, if you change the loading rate, you change the seismicity rate. That's more tricky to do with natural observation. So some years back, we looked at the effect of hydrological loading on deformation and seismicity. That was work with Laurent Bollinger and Pierre Bettinelli in particular, and Crustal, we talk later, has been working on that as well, Crustal Chana. So first, from geodetic measurements in the Himalaya, we do see variation in vertical displacement, but also shortening rates across the Himalaya, and it's a periodic variation that is due to the accumulation of water in the Gangetic plain, right? When there's monsoon, a lot of water is accumulating there, it's loading the front of the Himalaya, it's putting the Himalaya in extension, so it reduces the shortening rate across the Himalaya. So this process actually seems to modulate a little bit the seismicity, and it's consistent with the notion that the seismicity rate is proportional to the seismicity to the strain rate. If earthquakes were instantaneous, they would also respond to Earth height, and that's an old problem. I mean, already in the 19th century, a number of people like Alexis Perret and Schuster worked on that, and they assumed that they presume that actually earthquakes should be synchronized by tides. And here you have the blue lines. This is a sort of a spectrum of the periodicity observed in the catalog. And so there's a point here that indicates that there seems to be a small variation at 1 year. But when you look at all the constituents of the Earth tides, the blue lines, there's no significant correlation. The Earth tides are producing stress variation of the same order as tides, as hydrological loading. So you should have actually a very large response of earthquakes to the tides, simply because they happen over a short period of time. And so the stress rate is about 700 times larger than for the hydrological annual loading. So you should have a huge response. This is a clear proof that earthquakes take time to nucleate. Okay, they don't happen instantaneously. And this is a merit of the rate and state friction law that has been derived from lab experiments a long time ago, worked by Dietrich and Runa in particular. I won't go into the detail of that friction law, but the essential element here is that the friction is depending on the slipping rate, on the fault, and on the state variable. We have a hidden parameter, the kind of hidden parameter that Serge was talking about, which represent the healing. So this state variable is going to allow to have stick slip event, because when the slip rate is small, the fault heals, and then when the slip rate is fast, the fault is actually weakening. And with these two simple equations, you can actually produce a stick slip behavior. The thing is that the slip rate as a function of time increases gradually, so it's a logarithmic scale, so it stays very, very small for a long time, and then it accelerates toward the rupture. So nucleation takes time in this model. So this model has the merit that it can explain why we don't see a response to tides, and it has another merit, is that it can explain aftershocks. So let me explain how this works. So this is the time evolution of the slip rate for a single fault. And we consider two faults that are at different stages in their cycle. So one is slipping at a very, very low slip rate, and the other one is slipping at a larger slip rate. We apply the same stress change to the two faults. And we can show through the equation that the effect is that you suddenly jump from one sliding rate to another, and then you slide this branch here, and the rupture is advanced in time. If you do the same Coulomb stress change on that fault here, same principle, you're going to slide this part of the branch to here, and the earthquake would happen here. So result of that is that the time advance is not the same. The time advance of the rupture depends on how fast the fault was slipping in the first place. So now if you have a population of faults that would have produced regular earthquakes, and you apply a sudden stress change, then you have clustering and you can produce aftershocks with a 1/T decay, so the Omorillo and so on. So this is one merit of this formalism. Let's do a thought experiment here of increasing suddenly the stress on a fault. So we apply a ramp in stress, and we assume that we have a population of fault, and we assume that the faults were not necessarily critical. They were away, let's say it was a quiet area, and we suddenly apply a stress in ramp. It will take time to activate the fault, and once you activate the fault, you have a smooth increase of the seismicity rate. Then you have a plateau. The seismicity rate is proportional to the stressing rate, and then when you stop applying the stress, then it's going to decay, and that's the equivalent of the Omorillo. So we have tested the prediction of this model, not in the context of natural seismicity, but in the context of induced seismicity, where it's possible to have large variation in stress rate. So this is the context of Groningen. I should be careful with time. I'm going to be fast on that. So this is earthquakes that are driven by gas extraction from a reservoir that is at the depth of 3 kilometers. And the gas extraction actually is annual. They draw more gas in the winter than in the summer. So this is the rate of gas extraction. And on top of that, you have the seismicity. So nothing happened for something like 30 years after they started producing gas. And this is because the faults were not critical to get started. And then it increased nearly exponentially as a function of time. So let's see how our model actually can explain these observations. I won't go into the details of that because that's not necessary to understand the principle, but we do a model of Coulomb stress changes due to the gas extraction, and then we calculate the Coulomb stress changes on the faults that are offsetting the reservoir. So let me go straight to that slide. Yeah. So here you have a section, a seismic profile across the reservoir. You see that the reservoir is relatively narrow, about 200, 300 meters. It is offset by faults, and you have earthquakes actually in the interval of the reservoir. And there is stress building up on those faults because the reservoir is compacting as you draw the gas out, and you can calculate the Coulomb stress and use the geodetic data to validate all of that. Long story short, you can actually then test the model. You calculate the stress changes on the faults, you calculate the predicted seismicity rate, and you have only 4 parameters to actually adjust the model. And here you have the observed distribution of seismicity. And here this is the prediction from that model in space. Okay, so just like for the Himalaya, we have a good match. And here this is the match in time. So we take half of the catalog to determine the model parameters, and then we make a prediction for the other half. The blue line is showing the number of earthquakes every year that were observed in the field, and the cyan line is the best fitting model based on the inversion. And the black line is actually the variability that you expect from a Poisson process. So it works well. So and that validates the fact that we do need a nucleation time, so that is not instantaneous. Here, this plot is a bit complicated. It was invented by Schuster to test whether earthquakes are correlated with tides. You go around the clock in 1 year. Each time there's an earthquake, you make a step at the time of the earthquake. If the earthquakes are distributed evenly around the year, you go back to the origin after 1 year. And so if you repeat, you stay and you construct the path, you're going to stay around the origin. When you apply that to the data, you see that you're drifting away from the origin, so there's a strong seasonality in the seismicity with a peak seismicity in March. In orange, this is what we would expect if earthquakes were instantaneous. We would have a much stronger response of the seismicity, and the phase would not be right. The peak of seismicity would be in January, where they draw more gas, but the observed peak of seismicity is in March. With our model, we are on spot. We predict the phase and the amplitude of the signal variation. Okay. So this is to say that based on physics, we can do relatively well at forecasting the seismicity rate. The next step is, can we forecast, and that's going to be my last few slides, can we forecast individual events? That's really the difficult problem to solve to move to probabilistic time-dependent forecasting. So here, this is a very simple experiment. We take a very long fault, we use rate and state friction, and we model a seismic cycle on this fault. It's quasi-dynamic here, so we don't have seismic waves. We see that in this simple experiment, everything is homogeneous. We see that in this simple experiment, and here you see the slip rate on the fault, so it's similar to what I've shown for the Garca earthquake earlier. So you see slip pulses propagating along the fault. You can see that it's not periodic. It is actually a chaotic behavior. The segmentation is varying a lot. Each time you have a rupture, it redistributes stress, it affects the other area on the fault, and you have a self-organized actually complexity in the stress field that is resulting from that process. So what is in, and here this is just to show the complexity. So this is distance along the fault, and this is the slip rate, and you can see that it looks a little bit like the seismicity catalog, the paleo rupture we've seen for the subduction zone or across the Himalaya. And this is the time evolution of the moment deficit, moment release. It's a chaotic, complicated behavior. It happens that in this system, because the stress is self-organized, you can actually determine from just the instantaneous observation, the distribution of slip rate on the fault, you can actually determine if you are in a condition that would actually allow a large rupture to propagate. And we tested that approach based on the numerical simulation, and we can forecast. So here in red, you have the probability of, so those red patches are showing where the probability of having an earthquake larger than 7 in a period of time of half a year exceeds 50%. And the blue is actually the result of the simulation. The forecast is informed just on knowing at one time the state of the system. And you can see that you do a pretty good job at forecasting the ruptures with this approach. This is not applicable to real data. We would not know with enough uncertainties, with enough accuracy, the slip rate on the fault to make this practical. But it shows that there might be something to do if we can actually probe the state of the system. We tried something inspired by this finding in a simulation for the sagging fault. So here again, we have the sagging fault flipped horizontally. And this is a simulation based on rate and state friction. And you have here an example of a simulation that takes into account the fault geometry. And here, this is the observed past ruptures. You can produce very realistic, simulations with variable segmentation, similar complexity. And actually, in this system, from knowing the ruptures in the past over 200 years, we can make a forecast for the next 30 years that is pretty accurate. 80% of the ruptures are well predicted with this approach. So same principle as the previous slide. Red is the prediction from the model. On the black line are showing the simulation. So this is to say that by bringing some physics, we can actually, in principle, replace the lack of observations, the fact that we don't have long enough record of past earthquake to eventually move from time-independent earthquake forecasting, what we do in seismic hazard assessment, to time-dependent earthquake forecasting. Time to conclude. I hope that I've convinced you that geodetic data can be useful to inform us on where stress is building up to be released by future earthquake. Earthquake nucleation is not instantaneous. Rate and state friction provide a good, formalism to produce realistic earthquake simulation. but we are not there with regard to forecasting individual events. Thank you for your attention. Yeah.